Now the next set here. So previously we'd done physical properties and changes. Now it's about chemical properties and changes. The word chemical, of course, that's referring to just really things, objects, substances. And we're now going to look at what we mean by chemical and how it differentiates from physical. So when it comes to chemical properties, these are properties still once more that basically describes something's ability, this potential to undergo some kind of change of composition. Now, this is a little bit confusing at first, right? We'll see why. But let's go and see how we define chemical properties and see maybe how it compares to physical properties. For example, let's go and take a look at iron. Iron, I think you guys know what iron is, right? A lot of times metal things, maybe usually in the form of some very obvious metallic block or some sort of shape, and it's going to rust if it's in an oxygen-rich environment, right? And so after a while, it kind of becomes this dull red, cruddy looking thing, and not nearly as organized. Okay, sure. So the key here, again, is about this term composition. Does iron change into something else because of its environment? Yeah, because it was pure iron. Now it's iron and something else. So in this idea of iron rusting, that's a chemical property because we know that iron can do that if it were put in that position. Does that mean that we have to see iron do it every single time? If we picked up a pure block of iron right now in our hands, like if you imagine holding it, do you have to wait for it to rust to know that it's going to rust? Not at all, right? Because this is a property. If I know it does, if it's a property of another block of iron, it's also going to happen to my block of iron that I'm holding. Gasoline, same thing with gasoline. If I take gasoline and I heat it up to 200 degrees Celsius, it's going to burn, it's going to ignite, right? That is a chemical property. Why is that? Well, what that means is that I can take another sample of gasoline, right? Gasoline that's maybe at room temperature, not 200 degrees Celsius. That's pretty hot. If I take a regular room temperature sample of gasoline and try to burn it, right? Well, I don't have to burn it to know that it will burn, right? I don't have to put it up to this temperature for it to burn. That's a chemical property. It's a description of something that I know it will do something if I put it under certain conditions, right? It will change its composition if I put it under certain conditions. So that's what it means by property. It's something that could happen if I put it under certain conditions, but I'm not actually going to do it. Now, when it comes to chemical change, oftentimes we just use the word reaction instead. This is a change in which some substances that are involved will undergo changes that changes its composition, right? Whereas physical changes, right, all we did was kind of like tear it apart. We ground it up. We changed the phase. We didn't really do anything to it that changed the actual composition. So for example, sodium chloride. Sodium chloride, I can react it with silver nitrate and have it form some new thing, right? These are substances that are individually, salt, sodium chloride, silver nitrate, its own thing, and it becomes something new. Yeah, that's a chemical change. That's a reaction. It becomes something else. It's changing composition. On the other hand, gasoline combusts with oxygen to produce carbon dioxide and water vapor as another example. Yeah, that's the process of gasoline burning. So that is going to be an example of chemical change. At first, it was gasoline. Afterwards, it's something else. Hence, that's a chemical change. So it's a little bit different than a just property, right? Property is a description of what could happen. The change is saying that it has happened or this is what does happen when you make it undergo the change. All right, very slight difference, a little bit confusing at first. But remember, when it comes to the word property, properties are still about descriptions. And changes are more about the action. A couple of examples here. Let's talk about an egg. All right. Are there changes in composition? Once more, taking this idea about composition. So comparing properties and changes when it comes to physical and chemical properties. Now, let's go ahead and beat an egg. Right, we have an egg. What are some physical properties before and after the beating? Okay, physical properties. These are properties about what it is without having to change it. So I can take a look at these and maybe make a guess, or just use my eyeballs and even scent if you really need to, even texture if you want to describe this. Well, I think you kind of see here, you kind of have like nice deep red, orange, or deep orangish sort of yolk. You have a slightly yellower or slightly off-white, maybe even kind of yellowish egg white, and you have the even waterier part around it. Okay, sure. Those are physical properties that I can look at. I know that's what it is without having to do anything to it, right? Afterwards, right? As you look after it's been beat, right? The color changes a little bit more uniform. It's a little bit of this like sort of a richer yellow. It's got some bubbles in it. It's definitely got a texture that's a little bit different than what you might have seen in these distinct parts. Okay, right? Those are physical properties that I can make assessments of without causing any changes to what it is right now. What are some chemical properties before and after beating? Okay, all right, so chemical properties. Well, again, this is what happens when you cause the composition to change and then describing it. So again, based on experience, right? This is not something I can do just because I know what's going to happen, but based on experience and when it comes to cooking an egg, or excuse me, beating an egg, right? I know that it's pretty much just going to go from here to here. I didn't really do anything to it. I'm not really changing it. So let's kind of try this out. First of all, what exactly is in an egg? It's too simplistic for us to just say an egg is made of egg, right? That's not a thing. It might be that egg has a lot of water in it, right? Which it does. It also has a lot of different proteins, a bunch of different kinds of proteins. It does also have some technically carbohydrates. Let's do carbs, right? It's got some sugars. It's also got, by the way, it does have like several different kinds of proteins. So, and also, yeah, let's also get to some fats and lipids. Let's use the word lipids to make it more sciencey. So an egg is made of many different parts. I can't just say an egg is just egg, right? That's not exactly authentic to the question, what is in an egg? And so when it comes down to it, right, the chemical properties of this is that, I mean, if I maybe could like heat it up a bunch, it would cook. And it would cook a certain way. If I cooked it it would cook a certain way, right? This is a little bit harder to answer. Now, this is something that definitely relies on some amount of experience or at least some amount of extra information that tells you what happens to an egg as it gets heated. As it gets beaten. And so the way that they change is a little bit harder to answer. So this is just a hard question to answer right now. Overall, though, the key to this is this an example of a physical or a chemical change? Beating an egg. Well, I'm not actually changing the composition. I'm not changing how the water is there. I'm not changing how the proteins are arranged. Maybe I'm dispersing them a little bit, but I'm not changing the fact that some proteins are bonded to each other and afterwards they're bonded to a new carb or breaking proteins down into some other new. None of that's happening. It's all still there, just kind of rattled up a bunch, right? Using the whisk to whip it up. So ultimately, it's a physical change going from an unbeaten egg to a beaten egg because it is a physical action that does not change the individual composition of all the tiny proteins, all the itty bitty carbohydrates and lipids and water that's in an egg to begin with. Let's take a look at another example. Once more, an egg. An egg is now fried in this case, right? We're not talking about just whipping an egg. We're talking about taking an egg and then frying it. All right. What are some physical properties before and after the frying? All right. Well, once again, these are properties that you can identify without having to break apart anything or without having to do any extra tests. Just look at it, right? What kind of things do you see there? Well, you kind of see the same thing as before. The golden yellow yolk. You have the slightly yellowish white around it. You have the clear, waterier part around it. Okay, sure. After you fried it, right, you got a deeper, sort of, not deeper, but you definitely have that kind of rich yellow. Once again, this part right here seems a little bit more rubbery. It's a little bit flat. It's a lot more solid for sure. Definitely not all runny. And again, these are all properties that you can describe as you see it. What are the chemical properties? And this one's, again, kind of hard to answer because it's kind of hard to describe. But, you know, an example of one, it might be the egg, this raw egg. A chemical property is that if I were to fry it, it would look like that, right? That's a chemical property. I know that's what's going to happen because I've fried eggs plenty of times. I'm sure you have too. And so that's the change that occurs. Right. On the other hand, what is the chemical property of this? I don't know, right? And I've never really done any chemistry with a fried egg. For me to know, that's what's going to happen. Like I could take, for example, an acid and I can drip it on there, right? So let's say I have a little beaker of some dangerous acid. Right. And if I added that to this egg, right, I'm sure some change would occur. But I would have to actually perform that action to know what would occur. I don't know that at this point, so I have no idea what chemical properties there are for a fried egg. The point is, this last question, is this an example of a physical or a chemical change? Easily chemical change. Why is that? Because now you've actually changed the composition. So no longer do you have the individual proteins and waters and stuff like that that was in the original thing, right? And the lipids make it easy here. These have now been all sorts of cooked up and bonds have been broken and rebroken. All that heat and the oil that's being added to, all that stuff changed a lot of these properties. Hence why you have a completely different composition from before you fried it into now how it is after. So before and after, very big difference. Those are definitely some things to look out for, right? They can look different, right? So let's go back here for a second. Sure, the beaten egg looks very different than the original one. Okay, it changed a lot, but again, that's just a physical change because we didn't actually cause any of the proteins and carbohydrates and lipids to react. When it comes to the frying, though, we're causing all sorts of things to happen in the egg. Right? That's why it takes on a completely different set of properties. And yeah, you can be like, oh, well, it's still an egg. Well, not really, right? Because even though it is an egg, right, that's not still answering the question. It's all about the individual parts that make up this egg. Does that change? Do those things change in composition? And the answer to that in this case is yes. So to kind of just put this all together, at least when it comes to chemical changes and stuff, we usually use some specific terminology called reactants and products. You're probably familiar with this from before in previous science classes, but basically reactants are the things that are come together, they undergo changes and interact with each other. The products then are the results of these changes, and it basically always goes from reactants to products. And I've given you a couple of examples here, asking you to take a look at the sentence and identify what the reactants and products are. The first one says mercury oxide is produced when mercury metal is heated strongly in oxygen. So my reactants are the things that again are coming together. They're the ones that are the before, and then my products are the after. Well, it says mercury oxide is produced. That's been produced. So this is going to be my products. And then the mercury metal, that's a reactant, and then the oxygen is also going to serve as a reactant. Right? It was there before and is needed to make something called mercury oxide. The second one, water molecules are electrolyzed. They break down into hydrogen and oxygen gases. So what is the before? What is the after? Water is your before, so that's a reactant, and then it forms two products, hydrogen gas and oxygen gas. Pretty straightforward. All you got to do is pay attention to language, and you can pretty easily identify what your reactants and products are. Here's, by the way, an example of what that might look like, at least a still of the a video that might be from taking oxygen and mercury, combining those two and making mercury oxide. So go and take a look at these. You'll see that there's a lot of descriptions and lots of properties that go in with each of them, and it does a good job of giving you examples of physical and chemical properties. Right? We talked about chemical properties being a little bit difficult to identify at first because you have to see that happen. You have to know what it does, and without you knowing a lot about it, right, it's hard to make the conclusion. So this one just goes ahead and provides some examples of chemical properties that you and I probably wouldn't really never know, but because they have experience, it's a property and it's therefore universally applicable to any sample of mercury, any sample of oxygen, or any sample of mercury to oxide. And finally here, energy and changes in matter. When any physical or chemical changes occur, there's also a corresponding amount of energy change. Now, energy is a little bit harder for us to actually, explain. That's something we'll get to later on, but most of us have some understanding of it. Energy, first of all, is not an actual form of matter, right? Energy is not something that takes up space. It doesn't really have any mass that we can hold and measure. And so this energy is something that's an inherent part of just the physical state of something. We're not going to get into that now. Just know that, there's just some energy. So any change that occurs, there's always going to be some kind of energy change that also occurs. So when things react, energy is involved. Energy can be either absorbed or released by these chemicals or whatever you're doing when it comes to physical changes. For example, right, if I'm talking about boiling something, right, if I have a bunch of water in this and I want it to boil, right, that takes an energy input. There has to be energy added for it to become go from liquid anyway to a vapor. And that's going to be an example of energy being absorbed. And also, it's really complicated for that for you to go through and actually count for everything. Like, you can actually quantify, you can actually measure it, but that's going to be difficult for us to do. We're not going to be worried about it. It's more of a conceptual idea, which really leads to our third bullet point here. It says scientists rely heavily upon the law of conservation of energy. Right? Conservation meaning, conservation. We're not making and losing it. It's just there. We're just rearranging it. And so energy is neither created nor destroyed, only converted into different forms, right? It might not be obvious to us, especially to our naked eye, and especially if we're new at this, but just know that you have to have some conservation of energy. Otherwise, kind of the laws of our existence won't work out the way it's supposed to. So that basically breaks down the second part of matter, and that'll do it.